Hello, everyone. Thanks for coming this morning. So this week, actually, I cover for Prof. Raju. So it's the first week of ceramics. Okay, so this is my contact and my email. Anytime you can just email me. Okay, and these are the textbooks for the ceramics, fundamentals of ceramics. You don't really need to buy it. Okay, they're in the library, so you can just borrow from the library. Or okay. And these are the timetable. So I cover this week first and talk about the introduction of ceramics. Then start from week seven, okay. So which is 23rd of September, I'm going to talk about process, okay. Then after recess, so there will be process 2 of process of ceramic 2. Okay, so which will be week 8. For the tutorial, right, we have to be careful here because I realize you have one group is on Thursday, right? The other group is on Friday. Am I correct? Can you type, please? Because this calendar has been changed. I don't know for some reason because the old timetable set on Wednesday. But if I'm not wrong, let's double check. So one is on Friday, one is on Thursday. So this timetable is, this one tutorial one is for the Thursday one, because obviously you cannot have your tutorial before the class, right? Are you following me? So basically, which means the Friday one, the Friday group will be here, okay, tutorial one, but the Thursday group will be here. So this year is very weird, you know, because normally they will only put all the tutorial group either before or after the class. But this year is very weird. One group is before, the other group is after. Okay, so this timetable is for the Thursday group, okay, for the Thursday group, okay? So which means before the class group. So which means for the first week and second week, we're going to have a tutorial. After the third week, we're going to have another tutorial. And for the last 2 weeks, there will be the final tutorials, okay? So you just remember this. And for the October 14th, so it will be the quiz one for the Prof. Raju's part. Okay, so this was the CA1. So my part will be after everything. So which will be the week 12. Please mark your calendar. So this week 12. So so the quiz is cover everything. Okay, from just my part. Okay, my part, and also the format will be the same as final, just like a structured questions. Okay. Okay, so is it clear? So this one is very important. I think I sent a separate calendar to you already. So please, if you don't have, just a screen print, okay? Very important, especially these two quiz. Each quiz is 20%, so the final will be 60%, okay? Because this year we go back to normal. So last few years, there's only 6, but no final, okay? Okay, so the objective of this course, let's just start, okay, because I'm teaching ceramic, I'm Prof. Raju cover metal. So this course, we're trying to understand the general knowledge of the ceramic materials. So the most important thing is always trying to understand the concept between the process, structure, and the properties. Yeah, please highlight, okay? So this is, as I said, for most, this, let me just trying to highlight for you. Yeah. Okay, always these big 3 things. As I keep emphasizing in many different courses. Okay, so it's always about the 3 things: the process, the structures, and the properties. Okay, so all these big 3 things make full course of ceramic of the any materials course. Okay, so that's why I can say week 2 and week 3, I'm going to talk a lot about process, right? The process, okay. And week 4 and 5, I'm going to talk about these properties. So structure is something linked between these two, okay? And also we are going to get specific knowledge of the process of ceramics. So in this case, we're talking about very much about sintering, because compared with many other like polymers and metals, ceramic have something which is very unique, okay? Because they need very high temperature to sinter, S-I-N-T-E-R. Okay, center means you need to burn it at very high temperature. Okay, so these are the sintering, which is for the process, and understand and be familiar with property enhancement of ceramics. So in these properties, we very much focus on the toughness of ceramics. So why we focus on toughness? Because ceramic is fatal. They're so useful, you know, ceramic is very useful everywhere, like your computer, 90% of the computer, your handphone, actual ceramic materials. Do you know this, right? 90% of the materials are ceramic. It's very good for many reasons, like electrical properties, mechanical properties, and a lot of good properties there. But there's a fatal issue for ceramic, which is it's very easy to get brittle. Okay, so we have to think, we have to ask ourselves why ceramic is brittle and how can we overcome these problems. So this will be covered in week 4 and 5. Okay. So understand and familiar with property enhancement of ceramics. Okay, so this week is the easier week. Okay, it's just let you know some general things. So these are the introduction of the ceramic materials. Okay, so outline. So we start with the definitions. What are the structures? Some of the names, like what are the traditional and advanced ceramics. So there's some summary here. Okay, so this is just overall outline. Okay, then this part is important. Okay, VIP part. Okay, this part, crystal structures of ceramics. Okay, so we have to know the what determine the crystal structures. Okay, so the factors affect the structures for binaries and for some composite crystal structures. So what are the difference? What are the rules behind it to determine the crystal structures? Okay, and again, we're going to follow with the summaries. Okay, so the last one is characteristics. Characteristics of ceramics, some general things, what can be used. You can see ceramic is so useful everywhere for all sorts of applications. Okay, so that's the outline. So let's just talk about this week's outline. So we're going to understand the chemical bonds. What are the chemical bonds in the ceramics, and what are the crystal structures? As I said, this part is VIP, right? Important. So what determines the crystal of the ceramics? And the third one is calculate the minimal cut ion to ion radius ratio for coordination numbers. It looks very dodgy at this moment, right? Doesn't matter, but this one is important. Calculate a minimum cut ion to ion radius ratio. Okay, and then understand the crystal structures of some typical ceramics, and also understand characteristics and the applications of ceramics. Okay, so the important things are these 3 things. Okay, so these 3 are important. Okay, so we start with definitions. So what is ceramics? Okay, so ceramic is what? Ceramic is can be defined as a solid compounds that are formed by heat, right? That's what I said. So different from like metal and the polymer because they need very high temperature. So heat is the most important thing. So sometimes heat and pressure, you not only give them heat, but also give them pressure, right? So ceramic actually is very ancient technology, right? So you can see, so people use this to burn to sinter the vase, the rice bowls, all these things. Okay, so it's a very ancient technology, but it's so useful in the modern technology. Okay, and it must comprise with at least 2 elements. 2 elements. Okay, so provide one of them is non-metal, so which means at least you're going to have A and B. Element A and element B. Okay, so one of them, none of them have to be non-metal or non-metallic metal, while the other one may be metal or non-metal. So which means what? Which means no matter what, you always need to have a non-metal. Okay, you always have to have a non-metal in this whole compound. Okay, metal or non-metal, it doesn't matter. Okay, so the most important thing is in this compound, we will always have non-metal. Okay, for example, in this case, right? So magnesium is metal. Okay, oxygen is non-metal. But silica is non-metal. Carbon is non-metal, right? So the most important thing is you always need to have this non-metal. Okay, always need to have non-metal. Okay, so what are the metal and what are non-metal? You can see this is a periodic table. So this metal is this gray color. So all the rest just metalloid and the non-metal. We consider this as a group of a non-metal. Okay. Yeah. Continue. You can see these are the few very characteristics of ceramics, like oxide, very useful one, magnesium oxide, aluminum, iron oxide, barium titanate, cobalt fluoride, and aluminum silicate. Okay, and carbide, silicon carbide, boron carbide. Okay, and nitride. Okay, and boride. and also city side. Okay, so these are some very useful and very famous ceramics, okay, very widely used everywhere. Okay, and forms of ceramics, okay, so that's like a bug form, like this one. The bug form, like what you can see, like the rice bowl, right? The easiest one, the rice bowl, the bug, or the fiber, like a fiber, this silica fibers, or the synforms, like this one. This is synforms. Okay, so you can see this one, which we call a substrate. So we grow a synform on top of this substrate. So this part, this is interface. The blue one here is interface between the substrate and synform, and this is a thickness of the synform. Okay, so this is another form of ceramics. Okay, so nowadays a lot of people focus on this as synforms because it's actually the modern technology, like in semiconductor. People use synform all the time to deposit the ceramics on top of the semiconductor materials. Okay. So let's continue. Okay, so we finished the definitions of ceramics and forms of ceramics, okay? So now we move to an important part. So when we talk about crystal ceramic structures, right? Ceramic structures, they have many different levels. Okay, actually in all the materials, they have different levels, right? So the smallest one is the subatomic level. So what is subatomic level? Subatomic level, such as interatomic bonding, like what is this? It's ionic, or it is just a valence bond, or what is a valence? What is atomic model? And all these things is subatomic. Subatomic. Okay, so this is the smallest level. Then we talk about atomic level. So atomic level means structure combined of atoms. So how these atoms is arranged? For example, right, in this region, so the atom is arranged in a ordered way, right? So obviously this is what? Can you type? Can you type, Jonathan? Can you type your answer? Phone? Yeah, thank you, Jonathan. Thank you very much. Yes, correct, right? So this one is crystalline, right? Because it's very ordered. And this part is all very ordered, right? But how about this part? This part is a little bit like a random, right? So this one normally we call it a, can you type, Jonathan, again? Form? Yes, amorphous. Thank you, form. Thank you, everyone. Okay, correct. And also this one we call it a green boundary, Okay, so this is one green, this is another green. So you have many greens, right, in your ceramics, okay? So all the greens are ordered, but in between the greens, you have green boundaries, which is not ordered, okay? So this is atomic level. Then we follow about the nanostructures. Nanostructures, not about atom anymore. So this is a little bit higher, right? Higher, okay. Nanostructures, which means you have one dimension which falls into a nano range. For example, this one is a what? You must have seen many times already, right? Can you type? What is this? What is this? Tell me. Faster. Neo, Joe, Luke, Fang Hao, Mary. Yeah, don't be shy, right? I even just you. No, graphene, not graphene. Graphene is SMT, correct. Graphene is a sheet. Graphene is a paper. Remember, graphene is a paper. Graphene is a paper. This is CNT. It's a carbon nanotube. It's graphene roll up, become CNT. Okay, so just like you can imagine, this is graphene. Then you roll up, become CNT. Okay, so this one is CNT because this region, this diameter, is in a nanometer range. So one dimension falls into nanometer range, then we call it nanostructures. Okay, a range of small structures in the nanometer order. And then we follow the microscopic, this is a micron level. So for example, like this one, this is a green, right? So for example, this green, what is the green size? What's the green, this weight, this length? What are the green boundaries? You know, all these are in a micro region. Micron, okay, so it's 1000 nanometer, right? So another level, okay? Actually, for your FYP, most student FYP deal with this one, okay? Because if you want to say nanostructures, right, you have to use TEM already. Yeah, okay, so most of you cannot use, only the PhD student can use. But for your level, like next year will be FYP, right? You're going to use SEM. any microscopy to examine the microstructures. This is a level you are going to talk about. And the last one is what you can see. So that's what we call a macroscopic. Okay, so you can see, right, different levels. That's what we talk about in material science. You have to know every level. So what is a subatomic level? What is atomic level? What is nano level? What is micro level? So each level is going to determine its properties in different ways, right? It's very complicated. Okay, so these are the big pictures of the material science. Okay, so then we move to the smallest level. Smallest level is what? Is subatomic level. Subatomic level. So we have to know. So what is in the ceramics? So it is metallic bonding, or ionic bonding, or covalent bonding. So what are they? So how can we determine its ionic covalent? I think you have learned in your high school, right? But we just quickly review. Okay, so it's very much determined by this negativity. This is the one. So you can see from this periodic table, you know, right? This side is very easy to give up valence electrons, and this side is very easy to accept, right? So the more easier you can accept electrons, you're going to have a higher value here, right? You can see 4, and this is higher and higher, but this one is lower, right? This is only 0.9. Okay, so that's what we define this value. This is blue value here, which we call electronegativity, which means the relative tendency of the atom to accept an electrons, which means you're going to get electrons to become an ionize. Okay, so obviously the value is higher, you're going to be easier to become an ionize. Okay, which means you're going to accept electrons. Okay, so this one is ionic and covalent. And strong electron, sorry, let me just take this one. Strong electronegativity atoms readily accept. Okay, then let's continue. Okay, so obviously this side, right, the right hand side, you're going to have easy to accept. Okay, so the subatomic, we said we're going to determine whether it's ionic and covalent. Okay, so there are two types of chemical bond in ceramics. You obviously know, right? So both is going to exist. Okay, can you just please highlight? So these two, ionic and covalent, is going to, in most cases, is going to be coexist. Okay, so the B2 type, so the ionic you already know, right? Which means you have to give away, right? So involving a transfer of a bonding electrons, from electropositive cation to ions, electronegative. This is ionic. Then we have covalent. Co means we have to share, involving the orbital sharing of electrons between these atoms or ions. Okay, very simple. Let's just quickly. So this one, for example, right? This one is a very typical salt, right? Sodium chloride. Ionic bonding. So this little guy give away to chlorine. Okay, so occurs between the positive and negative ions. Okay, require electron transfer. So this electrons transfer. Okay, so and also why this is going to happen, so they must have a very large difference in electronegativity required. So obviously, if in a periodic table you are far away, which means one is on the left and one is on the right, then most likely you're going to form this ionic bonding. I remember the like sodium and chloride, right? So sodium is where? Sodium is here, right? Sodium is here. Chlorine is where? Chlorine is here, right? Very far away. Very far away. Okay. Okay, so let's see. So let's continue. So for this covalent bond, so you have to require shared electrons. Okay, so for example, like this carbon share the outer 4 with this hydrogen. Okay, so which means the electron activity are quite comparable. This one is covalent, so you have to share. Okay, so the most important thing here, actually, I just purposely just didn't write down. Okay, so can you please really write down? This is super important. In ceramic compounds A and B, most are partially ionic and covalent. Normally are more ionic. Okay, how can we determine? This is the equations. Can you write down, please? So we have to determine what's the percentage of ionic characters, so which is depend on these equations. 1 minus exponential minus 0.25 x. Do you still remember what is x? Can you type? X is the electronegativity. Very good. Very good. Yeah, electronegativity. Thank you, Jonathan. Thank you very much. Okay, electronegativity. So obviously, if the XA and XB have very large difference, so the ionic character is more or less, the percentage of ionic character is more or less. If XA and XB are very large, the difference is very large. So the percentage ionic character is high or low. Yeah, thank you, Fong. Thank you, Jonathan. Very good. Yeah, correct, right? Obviously, if these two are very big, all right, but the difference is very big. So which means this one is going to be smaller, right? Because there's a minus here, then you have to minus here, right? So will be, which means this one will be higher ionic character. So which means if X and B, A and B have very large difference in electroactivity, so the percentage of ionic character will be large, will be a lot. Okay, so that is the one we mentioned here. In the ceramic compounds, most are partially ionic and covalent, normally more ionic. And also the percentage, it is also one of the things, whether it is will be very covalent or very ionic. Okay, so this is the equations there. Okay, so let's continue. So you have already copied down this equation, right? Okay, so I move on now. Okay, so we just finished the subatomic. Subatomic, you just need to remember one thing. What are the one thing? Clarence? What are the one things here in the subatomic? Ceramic is a what? Ceramic have nobody answer this question? Answer? Clarence, Lee, Sanjun, Chang. Okay, summarize by yourself. Summarize for the subatomic is what? Subatomic is what? Subatomic is this red one. Okay, subatomic, most are partially ionic and covalent, and normally more ionic. Okay, okay. So these are the subatomic level. Okay, so now move to the atomic level. Atomic level, which we already said, right? So how the atom arranged. So you only have two types, right? Either it's very ordered or very random. So ordered then is what? Is crystalline, right? If it's random, which means amorphous. Okay, for example, these both are silica oxide, right? So silica oxide, this one is what? Both are silica oxide. Do you know what is this one? Like for example, this one is silica like what you use in the computer chips and everything, silica. But what is this? This one is also silica oxide, but it's what? Thank you so much, Sanjun, right? Am I correct to pronounce your name? Yes, Sanjun. Okay. This one is also silica oxide, but this one is what? Because the structure is so amorphous. So this one is glass. This one is glass. Okay. So that's why we said here, crystalline, most metals crystalline, many ceramic ceramic, except this little one, glass, which is this one. That's why sometimes we even say the amorphous we equals to, some people say glassy, equals to glassy, which means it's amorphous, which means it's very randomly. And the crystalline are some like polymers, okay? And amorphous, they have very complicated and very rapid. You can also obtain this amorphous structure by use rapid cooling. Okay, so this is this level, in this atomic level. So atomic level, you have either crystalline or amorphous. Okay, then in the crystalline, right, we have 7 crystal system and 14 crystal lattice. Okay, so you learn this in your year 1 material science class. So we have cubic, we have tetragonal, we have orthorhombic, we have hexagonal, we have monoclinic, triclinic, and rhombohedral. Okay, and in between we have simple, body-centered, feet-centered. Okay, so you have all these different type of 7 crystal systems and 14 lattice. Okay, so this is in the atomic levels. Okay, later we're going to spend a lot of time maybe next hour to determine, hey, how can we determine our ceramic can fall into one of them? Okay, so what are the rules behind it to determine the crystal structures? Okay, so that will be most likely will be next hour. Okay, so let's continue. Okay, so unit cell, this is a unit cell, which is the smallest region in space when repeated and 3D pattern of the atom of a crystals. Okay, so move on now. So now we move to the nano. Nano is easy to remember, right? We have 0, 1, 2, 3. 0, 1, 2, 3. 0 is what? 0, which means it's a dot. It's a dot. Just it's a dot, like a ball. Okay. So 0, which means everywhere is the same. Everywhere is the same. Okay. So 1 is what? 1 you remember most like a pencil, right? Like a pencil. Okay. So which is CNT, right? In this case, it's CNT. So because you only have one dimension, which falls into a nanometer range. Okay, because this length could be even microns or even centimeters. Okay, and this is 1D. I remember 1D is a nanorod or nanowires, and it is a pencil. Okay, 2D is what? 2D is just like a pen, like a paper. Okay, 2D is a paper. Okay, so it's a thin film. Okay, because you have this diameter and this diameter, which is in a nanometer range. Okay, sorry, this diameter. So it's 2D, so it's a paper. Okay, and then all the rest, some people call it a 3D or special structures. For example, like a micro mass porous, your pore are very small. Like your pore, if your pore is in the nanometer range, so it's a 3D structures. And also the core-shell structures, you have particles, but you have a shell on top of the particles, like core-shell structures, or some like hybrid structures, organic, inorganic, and nanocomposite and nanograin materials. Okay. And okay, so we finished the finish the nanostructures, right? Nano is what? 0, 1, 2, 3. Very simple, right? 0, 1, 2, 3. Okay, what is crystal? So crystal is either amorphous or crystalline, right? Then in crystal you have 7 and 14. Okay, remember all these small things there. So now we move to the micro level. So micro level is, as I said, will be more likely deal in your FIP. Okay, because you can only use SCM in your FIP. TEM is too expensive, okay, and also need a lot of trainings. So most likely you're going to use SEM to determine the microstructures. So when you are given a project by your supervisor, so then your supervisor say, hey, tell me what is the microstructures of these materials. So what are you going to say? Okay, so these are the things you are going to say in your FIP. Okay, so for example, what is the shape and size of the grains? How big is the size? So it's a round shape, or it's a hexagonal shape, or the square shape, whatever shape, right? The shape and size of the grains. And do you have any pores here? Your pore is here, or your pore is here, or your pore is here. Okay, so where is the pores? What's the percentage of the pores? So do you have any second phase, like impurities? Do you have any other impurities, like dopants? So where are they? So these distributions, all these things is you're going to supposed to tell your supervisor when you do your FIP, hey, okay, I have fabricated these materials. I have already done the SM. So now I share you. So what is the size of the grains and what is the porosity, the percentage, any grain boundaries, any impurities. So what are distributions? Distribution is very uniform. I just focus on somewhere. It's focused on the grain boundaries, or it's in the grain it's inside the grain. All these are very important, useful informations for you to understand the properties later. Okay, so this level is microstructure levels. Okay, this one is important because it's useful for your FIP. Because otherwise, right, every year we're going to FIP. A student said, hey, I don't know what I'm going to say in the SEM. So these are the exact things you need to say using SEM. Okay, you need to share with your supervisor. So what are the microstructures of your materials? Okay, and there's some names here. So what are the traditional and advanced ceramics? Okay, traditional one is many years ago, like 20 years ago, people spent a lot of time study this traditional one, like normally, how can we differentiate traditional and advanced ceramics? So it's more or less related with structures. Okay, so if you control the structure in a very good way, so then we can say it's a more advanced ceramics. If you can't control the structures, so it will be traditional. Okay, so if the structure is very coarse, very non-uniform, everywhere is different, and you have all sorts of different phases. So this one most likely is a traditional one. But if you can control your process in a much better way, so now the structure is one order of magnitude finer, much smaller, and very uniform, and much less pores, which means you can control in a much, much better way. So that's the strength of material scientists. Then you say you have advanced ceramics. So this is our strengths, okay? This is what material scientists can do, because we can control the microstructure in a much better controlled levels. Okay, so then this is advanced ceramics. Okay, then like traditional ceramics, for example, like white wells, refractories, right, and also bricks and tires, variation, right, and also using the concrete and the abrasives. Okay, so these are traditional ceramics. But advanced, you have so many, right? You can say so many, for example, functional and structure. So advanced ceramics, we're going to have two types. One is functional, one is structural. Okay, functional and structural. So what is functional, what's structural? So you just need to remember one thing. Structural means your materials have to deal with the mechanical. You have to deal with mechanical. You have to deal with mechanical strengths. Okay, so this one is very important. Okay, this is structural. So automobile, tribological, bioceramic, and the nucleus. Okay, for example, in all these applications, it's very important because you have to make sure your material is strong and tough enough without fail, right? Obviously, can you imagine if you use material in nuclear, it cracks, horrible, right? So this one is very important, this form structural. So anything, if it's not related with mechanical, so we say it's functional. Anything non-mechanical, so it's functional. For example, we can use for the as a substrate, as a piezoelectric, magnetic, optical, anything can be called as a functional materials. Okay. So that is the advanced ceramics. Okay. So that's what I put here. Okay. So summary. Now we come to summaries. Okay. I help you to review. Okay. Let's start. So what is ceramic? What is ceramic? Ceramic must have what? Have A and B, right? So no matter what, one of them have to be what? Can you type? Thank you, Clarence. Have to be non-metal. So that's the first one. Ceramic is always have to be more than one. Must be AB, at least AB can be AB, C, D, or can, but at least AB. Okay, we only talk about the lowest limit, AB. So A can be not metal or non-metal, B have to be non-metal, which means no matter what, the B have to be non-metal. Okay, so this is a ceramic definition. Then we said we have different levels of structures: subatomic, micro, sorry, in between you have a nano, micron, and a macron, right? So in subatomic, we said ceramic is a what? Ceramic is a joint of covalent and ionic. Okay, so that's the sub level, which is most ionic, can be partially covalent. Why this one is important? Because later this one is useful. Later we're going to share with you why it is important. So ceramic is most ionic, can be partially covalent. Okay, then we move to the atomic level, right? Atomic level is what? Atomic is big one is what? You have what? Your atom is ordered or non-ordered, right? Okay, so you either have a crystalline or amorphous. So in the crystalline, you have several crystal systems. Okay, so this is atomic level. Then we talk about the nano. Nano what? Nano, you always need to remember what? 0, 1, 2, 3, right? 0, 1, 2, 3. Okay, so that's nano. Nano 0 is a what? 0 is a nano dot. 1 is what? 1 is a pencil. 2 is a paper. 3 is any other things. Okay, so nanodot, nanowire, thin film. So that graphene, I want to mention about graphene. Graphene is obviously it's a 2D materials, okay? And 1D is like a CNT, okay? And 3D is any other things. Okay, this is nano range. And in the micro, as I said, yeah, in your FYP, you might use a lot, okay, micro. So you have a grain size, shape, distribution, grain boundaries, and the pores, anything second phase. I haven't finished, you can write them by yourself. Okay, so micron level, you have grain size, shape, percentage, pores, second phase, impurities, all these things, which is one you can see by your eyes. Oh, sorry, by the SEM in the micron range, okay? And the macron is what you can see by your eyes, okay? So that's why we don't put here. So these are the summaries, okay? Then we talk about what is the advanced and traditional. So advanced and traditional, the only difference is advanced have an order of magnitude finer and uniform, which means you can control your process in a much better way. So everywhere it becomes much more uniform and become much finer. Okay, so this is advanced ceramics, okay? The last one, what is structure, what is functional? Structure is what? Structure is mechanical, mechanical, non-mechanical, which is structural. Okay, so can you write down or just screen print? Okay. So these are the summaries of the part one. Okay, so we move on. Simple, right? Normally first week is always very simple. Okay, it's a happy one. So two, crystals, this one is important. How can we determine the crystal structures of the ceramics? So this is what level? Is subatomic, atomic, or nano, or micro? Can you type? What level? Clarence, Sanjun, please answer. Jonathan, phone. Aaron, and Anson, sorry, Anson. Yeah, correct. Thank you very much. Thank you very much. Correct. This one is atomic level. So now let's see, how can we determine the atomic level? Okay, crystal structures. Okay, so there's three factors affect the crystal structures. Like number one, crystal stoichiometry. Number two, radius ratio. Number three, propensity for covalence and the tetrahedral coordinate. Looks, even I can't pronounce well, right? So it looks very dodgy. No worry, later I'm going to explain this one. Okay, so these three factors affect the crystal structures. The first one you know, right? First one is very simple, right? Crystal stoichiometry. So what are the crystal stoichiometries? So which means you just need to remember it's all about charge balance. Charge balance. For example, like alumina. If you have alumina 3 plus, right? 2 alumina 3 plus, which means 6 plus, right? You must balance with 6 minus, right? So which will be balanced by 3 oxygen 2 minus. Okay, so this is just simply charge balance. You know this from day one. Okay, so charge balance. So what are the stoichiometries? So what we call is a specific ratio between the cation and ions. Okay, like 2 and 3. You must maintain a balance between the positive and negative charge. Okay, so that's what we said, the stoichiometries. Okay, so anyway, it's all about charge balance. Okay, so this one is so universal. So you think you learn in your day one in high school. Okay, so this is the first one. So the second one, okay, and also there's another concept here. How many ions surrounding a cation is called Cornish number. So for example, we have an ion. So have to surround it by a few cations. So what are the numbers? What are the numbers of the ions in contact with the cations is called Cornish numbers. Okay. So for example, in this case, okay. So and also the second one is for example this one. So you have a ion here. Okay, and this is cations. So obviously the Cornish number is 1, 2, 3, and 4, right? So this is just Cornish number. Okay, so how can we say the atoms, the ions and cations, how they pack together? So normally ions is larger. Ions are larger, right? Because ion is accepting ions, right? Because that's still electrons from others, right? So bigger, it's bigger. So ions normally is a bit bigger. So we always first pack the big one first. You make the ions big, close packed first, okay? So ions usually larger and close packed. Then cation is just small little ones. On the other hand, usually smaller. So they will just go where the space is. Okay, for example, my ions have already packed. So then the cation just go into the space. That's what we call interstitials in the crystal lattice between the ions. Okay, so that's the position. So normally we always pack the ion, then the cation just go in between. Okay, so this is the one, right? So there come a very important concept. What is the Vidas ratio? This one must be very new to you. Okay, so just be patient. We're trying to learn the things here. Okay, Vidas ratio here. Okay, so there's a very important concept here. Concept here is, this is super important. Stable ceramics, crystal structures, you must make sure the ions surrounding cations are in all contact with that cations. So what does this mean? Which means no matter what, your ions, which is this big one, right? Ions, must be in contact with the cations. So for example, A, B, C, right? So which are the one in contact? A, B, C, which one? Can you type? Phone? Clarence? Jonathan, thank you very much, right? So B and C is in contact, right? Correct, right? Contact, 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 right? Okay, which means these two are stable. Still, which means it's possible. It's possible. Okay, correct. Okay, but if they don't contact, like in this case, A case, so it's not stable. So which means this one will not exist. Okay, so this is first important thing. So important thing, always remember, in a stable ceramic, okay, ions surrounding cation have to be in contact with that cations. So now my next question. Okay, which one, since now we have two scenarios, from B and C, right, are both in contact, right? Okay, so which one give you the lowest, remember, lowest Vidas ratio of the cation to ions, which means RC over RA, RC over RA. So which case is going to be the minimum? Can you type? ABC. Phone and Jonathan said B, correct, Mary, thank you very much. Excellent, excellent. Which means what? Which means the B give you what? B give you for specific coordination number. In this case, all the coordination number is 4, right? All are 4. For specific coordination number, there is a minimum or critical this kind ion ratio, RC over RA, for which this contact have to maintain, right? Obviously, right, in this case, right, for example, in this B and C, right, the ion are roughly the same size, right? Same size, but this RC over RA in B case is going to be the minimum, because this one, which means everywhere you have to in contact. This is contact, this is contact, 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 contact. So except the cation and the ion have to be in contact. This is the stable case, right? But in the minimum case, which is ion is also in contacting with the ions. So this one is going to be the minimum case. So why this one is important? Why this one is important? It's because this one is the only one you can calculate. So later we're going to calculate this minimum one, this RC over RA. Remember, RC over RA is the contact, not only between the cation and the ion have to be maintained, but also the ion and the ion have to be in contact. Okay, clear? Correct. Okay. So let's continue. Okay. Okay. So this is a super important tables. Okay. So this is Vidas ratio. If the Cn number is equals to 2, So RC over RA have to be less than 0.155. If it's 3, have to be in this region. If it's 4, have to be in this region, which means what? Which means RC over RA is super important to determine what? Can you type? Super important to determine from this table, super important to determine what? Mary? Thank you so much. Thank you for obviously, right? Have to determine this CN number. So RC over RA is an index to determine how your atoms is going to be in contact with each other. Is in this tetrahedral way or tetrahedral way or octahedral way or cubic way. Correct, right? So if RC over RA is less than this one, it's going to be 2. If RC over RA is equals to 4, or if in this region is tetrahedral. So the things what you can calculate RC over RA is always the minimum one. Minimum one is which one? Minimum one is this one, 0.14, 0.732. Okay, so now let's see. So we can calculate one of them. Okay, so I show you examples. Okay, so let's continue. Okay, this table is super important. Why is so? Because once we know RC over RA, because RC over RA is you can get from the reference book. You can just simply get, just look at the reference book. What are the RC over RA of this compound? If you know, if my RC over RA is 0.5, if it's 0.5. Okay, so what connection number? Can you type? If my RC over RA is 0.5, what connection number? Type. Phone. Mary. Clarence. Everyone. Stephanie. Thank you very much. Thank you, all of you. Yeah, correct, right? If my RC over RA is 0.5. The coordination is what? Coordination of this CN equal to 6. Okay? Okay, correct. Okay, so now let's prove this one. Why when the RC over RA is certain value give you this number of this coordination number? Okay, so now let's prove it. So so demonstrate that the minimum kite ion RC over RA for coordination number 6, which is 0.414. 6 is something like this, right? 6, 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6. Okay. So 1, 2, 3, 4, 5, 6. Okay. So now, if we want to calculate, is RC over RA. Remember, minimum is what? Minimum. So minimum is not only your kite ion and ion have to be in contact. That's a stable case, right? The stable case. Okay. But what? But your ions and ions is also have to be in contact, right? So that will make the minimum case. So once you have such things, right? So it's just a geometry you learn. You want to learn in your high school, right? Okay, so now let's do this calculation together, right? Because now everywhere have to be in contact. So let's do this together, right? Okay. So this is 6. Coordination number is 6. Like in this case, right? Coordination number is 6. So we just get the middle one here. So then we will see this one, okay? So then one of the face of crystal with ion is just touch along the edges, also the face diagonals, okay? So for example, we have GH and HF and GF. So this is the triangle, right? The triangle, so G, so this one is what? This one is R, this one is RA, right? This one is R, C, right? This is Kion, this is RC, this is RA. This one is what? GF is what? GF is what? Can you type? GF? Clarence? Handsome. Thank you very much, Jonathan. Thank you all of you. 2RA, right? Correct, right? Simple. Is it simple? Correct, right? Okay, so we said GF equals to 2RA, 2RA. Okay, so then FH, GH equals to RC plus RA, right? Correct, right? So it's just a simple 45 degree signal, right? So if you want just a GH square, FH square equals to GF square, okay? So put everything in IA plus RC square plus RA plus RC square equals to 2RA. I give you 2 minutes to calculate. Tell me the value. 2 minutes. Count down, 2 minutes. What's the value here? You have a calculator with you, right? So what's the relationship between RC over RA here? Anyone you finish this one, could you please type here in the box? I give you 5 extra marks. Just joking. Okay, anyone finish the calculating? Found how? Nadia? Go, Kang Hao? All of you? Phone 225, is it correct? Joe? Neil, everyone. Stephanie, all of you. Clarence, Jonathan, what's your answer? 414? Go count 414. We are. Okay, I give you half minutes. Extra half minute. Okay. Okay, so just follow from here, right? So RA plus RC. So then this one we just get 2, right? 2 here. So then we just put a square root on both sides. Okay, so which in the end will be RA plus RC equals 2RA over square root 2. Correct, right? RA plus RC equals to 2RA over square root 2. Okay, so the RC over RA equals to 2 square root 2 minus 1 equals to 0.414. I give you round plus. Excellent. Okay, excellent. Okay, okay. 414. Is it correct? Can you check your table? Can you check your table for the coordination number 6? What's the minimum value there? Yeah, check your table. If you're cheating, you can also cheat, right? You don't even calculate, you're cheating. Okay, you can. I'm just joking. Okay. Yeah, it's 414, right? Correct, right? From your table, you know, for the coordination number 6, the minimum value should be 414, 0.414. Okay. So this is a calculation, and I leave you to calculate this when the coordination number is 8. So what is RC over RA? Okay, so let me see. Yeah, derivation tested. I will talk about the details of the testing later, okay? Don't worry, okay? So RC over RA, so this is tutorial 1, but so you just go back. This one anyway is a proof question, so it's easy, right? So you know the answer already. So you just need proof. RC over RA is 0.732, correct, right? So let me okay, finish here. Okay, so now you're happy, right? We have already learned 2 rules for determining the crystal structures. Okay, first rule is what? Can you type? First rule? Can you type? First rule is the charge balance. Yeah, okay. First rule is charge balance. Okay, thank you. Thank you, Jonathan. The second rule is the RC over RA, right? Okay, good. So that's why I already asked you, right? If my RC over RA is 0.5, so what the coordination number here? So most of you answer 6, right? Correct, right? Because according to that table, I know the RC over RA is 0.5. So according to that table, I know my coordination number is supposed to be 6. Correct, right? Okay, but there's always a but. Okay, that is the rule 3. Rule 3 is a special thing here. Rule 3. Okay, in rule 3, so there's a propensity for covalence and the tetrahedral coordination number. So look, very lousy, right? Propensity for covalence, which means what? You still remember, right? We said ceramic, most are ionic, correct, right? Most are ionic, but they could also have some characteristics of covalency bond, correct, right? So in some compound, so maybe they have a little bit more covalence bond there. Okay, so that table is not working anymore. So for example, just as I mentioned, right, the AB, I know the RC over RA is 0.5. So according to that table, it's supposed to be 6 coordination number, right? 6. But the reality, it is only 1, 2, 3, and 4. Only 4, which means they have this tetrahedral coordination number. Okay, so why this one is going to happen? Okay, it's because you have more covalence bond already now. So that table is no longer valid. Okay, so this is a special thing here. Okay, so which means the table we have drawn together, right? We have just calculated. We know that's RC over RA. We calculate RC over RA. We're going to know the coordination number, but very special thing here. But to be very careful here. Okay, remember that one only applies to very ionic case. That table only applies to very ionic case. So if you have covalent bond, so you have to be very careful. Okay, so in many compounds, that's what we say here. In many compounds, the tetrahedral coordination number is observed despite the radius ratio would predict otherwise, which means just as I asked you, if RC over RA, now according to that table, if it's 0.5, so everyone just look at the table and tell me the NC is supposed to be 6, right? But the reality, it is no. It is not 6, it is actually 4. So then why it is so? Why it's not 6 anymore? Because that table only applies to for very ionic case. So this situation typically arises when the covalent characters of the bond is enhanced. Such as what? Such as if the in the periodic table, if the closer, if the neighbors, right? So then it's different. It's closer electroactivity. Okay, so maybe we stop here because it's 10:30 already. So we have a 10 minutes break. 10 minutes break, okay? We come back later. And I leave this one for you to copy down if you haven't copied. Okay, see you 10:30. 10:40, sorry. 10:40. Hello. Yeah, so let's continue. So the first week is, as I said, always a simple one. Okay, so let's just quickly, first of all, quickly review. So we already learned that ceramics AB, right? So one of them. So the most important is B have to be non-metal. So the rest I don't care. Okay, and we have 4 different levels. Subatomic is most ionic, but it's partially covalent. So just as we said, right? So if that periodic table, so only applies to very ionic case. If you're a little bit more covalent, you have to be very careful. Okay, so atomic, crystalline, and amorphous. You have nano, 0, 1, 2, 3. Micron, you have all these things. I just write a few. You have to fill all of them. Okay. And what is advanced and traditional? So advanced traditional just orders of magnitude finer and uniform. Okay, and the structural and functionals, which is mechanical and non-mechanical. So that's the difference. Okay. And also we learned how can we determine crystal structures. So we just finished these 2, okay, charge balance and radius ratio, RC over RA, right? RC over RA. Always remember, we always talk about the minimum case, minimum RC over RA, because this is the one you can calculate, okay? So then RC over RA only applies to, you come out the table, right? Only applies to very ionic case. For example, so we set this one. Yeah, prefers to very ionic case. Okay, so once we know this one is quite ionic, then we know if you know this one is 0.5 here, right? So which means most likely it's going to be Cn equals to 6. Okay, so that's the charge balance, and also the rule 2 determines this. Okay, but if you have a little bit more covalent bond, which means your A and B very close in the periodic table, so you have to be careful. So if you have more covalence bond, So for example, you have this copper, aluminum, zinc, and also this other, there's a few ions, the COSA, electron activity, or sp3 hybridization, silica carbide and germanium, these three things. Okay, so you have to be very, very careful. So even your RC over RA tells you you're supposed to be 6, but the reality is what? Tell me, can you type? The reality is, can you type, Jonathan, Clarence, everyone, phone. Jonathan, thank you. Any more answer this, because this one is so important. So important. This is tricky, the only tricky things in this part, in this section. Only Jonathan know. Yes, thank you, Saint John. Okay, Saint. Okay, thank you. I can't pronounce your name. Sorry. Yeah. Okay. Doesn't matter. Okay, it's tetrahedral. Tetrahedral, which is 1, 2, 3, and 4. Okay, so it's not 6 anymore. It is 4. Okay, so that's a special rule. Rule 3. So rule 3 is always a special and unique thing here. Okay, so now let's see. For example, you can see, right? If this kite iron is here, kite iron is this copper, zinc, aluminum, all these things right here, and your ion is here. So they're very close, right? Little brother, very close neighbor. So that's why they have more covalence in between. So you have to be very careful. So Cn is equals to 4 now. Okay, continue. Okay. So now I give you a few examples. So first of all, rock salt. Sodium chloride. Can you check the periodic table? So it's very ionic or have a lot of covalency. Can you type? This one, right? So everyone use as a example for what? For ionic lah, right? So now I'm telling you, thank you, Fong. I'm telling you the reduced ratio is 0.56. So can you check the table quickly, Fong, please? What is the coordination number, Fong? Just according to that table, what is coordination number? So I tell you, because I can get all this value from reference book, right? 0.45. Thank you very much. So it's 6, right? So 6, correct. Let's see, is it 6 or not? It is 1. Where's my mouse? Oh, it's here. 1, 2, 3, 4, 5, and 6. Correct, right? Correct. Okay, correct. Because it's so ionic, so we can very safely use that table. No worry, hassle-free. I use that one. So 6. So you can see this one is a very typical, what we call is a rock salt structures. So rock salt structures, how can you remember rock salt structures? So if you just take out the black one, so you will see is what structures. This is very typical what? If I take out all this red, the black color one, take out all this sodium here. So the chlorine is what? What structure? It's very typical. It's not BCC. It's not BCC. Not BCC. This one is what structure? You have one here. BCC you do. This one is FCC. Fifth and dot. This is FCC structures. FC. Yeah, thank you very much. Yeah, FCC. So this one, the rock salt, is just more or less like if you have two orange FCC and black FCC together, interpenetrating each other. That's what we said, penetrating FCC together. Okay, this is rock salt. Okay, so let's continue. Okay. Okay, so as I said, right, use all this table, you can see, right? So this is the second one. Cesium chloride. Cesium chloride, you go and check your table. Cesium chloride is again is what? Cesium chloride. No, it's FCC interpenetrating. So both are FCC. Both are FCC. Okay, the red and the black are all FCC. Okay, interpenetrating. Yeah, just like two FCC just interpenetrating together. Okay, so that's the rock salt structures. Okay, so now we move to the cesium chloride. So cesium chloride, please check your the periodic table. Is what? Cesium, where's cesium? This cesium is here, right? Cesium chloride and chloride is here. Again, our distance and most distant neighbors, right, are so far away. So obviously it is very ionic. So, and also we know that is 0.94. So what is connection number? Tell me. What connection number? Yes, correct. Okay, so connection number is 8, right? According to that table, so far, rock salt and cesium chloride, very happy use that table. We know that connection number is going to be exactly follow that table, right? Because it's very ionic. Okay, so then this one you can see 1, 2, 3, 4, 5, 6, 7, 8, 8, okay. So you can remember this one as a BCC. So BCC is something like this, right? BCC, you have 8 in the corner and 1 in the middle. But this one obviously not BCC, right? You just remember as a BCC, just help you to remember, okay? Because these two are different. It's different. Okay, so the cation ion is in the middle. Okay, so this is another type which we call the cesium chloride. Okay, connection number is 8. Okay, so let's continue our cesium chloride. Okay, so zinc blend. So zinc blend, zinc and sulfide. Okay, so the radius ratio is larger than 0.414. Larger than 0.414. Can you check your table? So what is supposed to be its connection number? If it's larger than, right, so actually it's, according to that table, it's supposed to be 6, correct, right? Thank you for now. Okay, but then can you please check your periodic table? The periodic table shows you zinc. Where's zinc? Zinc is here, right? Zinc is here, and zinc and sulfide is here. So most likely, wow, so close, right? Most likely they have a lot more covalent bond in between. So it's which rule now is going to take over? So it's not rule 1, not rule 2, it is rule 3. Rule 3, because you have more covalence and bond in between. So you are going to have 1, 2, 3, and 4. Correct, right? So connection number is 4. Okay. So this is the unique thing here. Once you have more covalent bond, make sure use that table very, very carefully, very cautiously. Okay, especially you know that if it's going to be 6, you have to be very careful. Only the 6 case have to be very, very careful. So most likely, if they're very close in the periodic table, so most likely it will be 4. So this one is a zinc blend structures. Okay. So okay, so we cannot use this anymore. So it's 4 is here. Okay. So okay, so that's what we just again read through this one. This is a rule 3, propensity for covalency, which means if more covalency, yeah, so it's going to be number 4, which is going to be heterohedral coordination number. So I'll give you the example, which is zinc sulfide, which is zinc blend. Okay, so that is rule 3. Okay, so now we move to the last one, which is a composite crystal structures. Like for example, this one is a ABC. So before we only talk about the binary, which is only AB, but now we have ABO. For example, this perovskite structures are calcium titanate. So calcium titanate is quite special, you can see. So they have this ABO3, which means they have 2 cation ions and only 1 ions. So the smaller cation ions is going to be in the middle, which is titanium. Titanium is here, okay, B is here. So then that's what we say here. The lattice parameter of this one, which is 3.8967 Armstrong. Okay, so which means 0.4, roughly 0.4 nanometer. Okay, so this is just this length. Okay, it's roughly about 0.4 nanometer. Okay, this is lattice parameter, and the name is perovskite, and the smaller titanium, which is B, which is in the body center. Okay, and the bigger this cation ion, calcium, is at the corner. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and also you have I ions, which is at the feed center here. Okay, so this is a perverse spec structures. Okay, so in this type, because it's becoming more complicated, so we just need to know one thing here is how can we determine the numbers of the ions in one unit cell? One unit cell. Okay, so obviously, right, in this case, so how many titanate here? How many titanate here in one unit cell? This one is very easy, right? How many titanate here? Because in the body center, yeah, correct, right? Thank you, Jonathan. Thank you for you only have one, right? Because this full whole smaller titanate is inside the body center. So all of it belongs to this cubic centimeter, okay? Belongs to this unit cell, so it's one. But then how about calcium? How many calcium in this unit cell? Can you type? How many A in this unit cell? Fong said 8. Jonathan said 3. St. John said 2. But is it possible? Because my compound is A, B, O, 3. So if I B have only 1, A have 3, or 2, or 6, do you think it's possible? Yeah, okay, Jonathan. Okay, I know you now. Okay, phone set. Okay, good. Okay, now let's move on. Okay, so that's the tricky thing here. We have to calculate. Okay, so how can we determine the atomic number? Okay, so in the body center, it's very easy, right? Because in the body center, this whole little guy belongs to this unit cell. It's very easy, right? But now it's different. If you stay at the corner, okay, like this one, right? Like this calcium stay at the corner of A here. Okay, so now obviously this calcium you stay at the corner, which means you're going to have 8 neighbors. Okay, the top you have 1, 2, 3, 4. The bottom you have 1, 2, 3, 4, which means only this one atom is shared with 8 neighbors. So which means you only have 1/8 belongs to you, right? Correct? Okay, so that's what we said here. So if you stay at the corner, just like the calcium there, okay, corner, so it's supposed to be 1 out of 8. 1 of 8. Okay. So, but now if you stay at the edge, in this case, like edge, this is edge, right? If you stay at the edge, so you're going to have share with 1, 2, 3, and 4. 2 on the front, 2 on the back. Okay, so if your atoms stay at the edge, so only 1/4 belongs to the unit cell. Okay, but if you stay at the face here, like oxygen case, right, face here, so you're going to have 1 and 2, left and right is going to share with these atoms. Okay, so that is how we can determine the numbers of atoms in one unit cell. So if you stay at the corner, so you're going to share with 8 units. Okay. Can you show the edge in the lattice structure? So edge is here. This is edge. Okay, so this is corner. So shared by the 8th unit. So it's 1 of 8, 1 of 8, okay? So if it's edge, right? So shared by 4 units. So it's only going to be counted as 1 out of 4, 1 of 4, okay? But if it's a face, shared only by 2 units. So you're going to count as 1 out of 2, okay? So that is how you can calculate. So now if we go back here, right? Go back here, this one. So now I know this calcium stay at what? Tell me. Calcium stay at what? Can you type? Calcium stay at the corner or face or edge? Yeah, thank you, Anson. Thank you, Anson. It's corner. So it's supposed to be, because it's corner here, right? So which means it's supposed to be only count as how many in one unit cell? Can you type? Anson? If it's corner, 1 of 8, right? Correct, right? So it's only supposed to have 1 out of 8 belongs to this unit. But how many here? I have 1, 2, 3, 4, 5, 6, 7, 8, right? So which is 1 out of 8 times 8. Okay, altogether, I'm going to have 1 calcium here. correct, right? Okay, now let's see the oxygen. So oxygen stay at what? Stay at the edge or at the corner or the face. Can you type? Oxygen, yeah, oxygen form. Oxygen stay at what face or what face? Face, correct. So it's supposed to be how many? If you stay at face, so only consider as 1 out of 2. Thank you very much. 1 of 2. 1 out of 2, correct. 1 of 2. So 1 of 2, 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 1 of 2. Okay, so you have 6, 1 of 2, which means you're going to have 3. Correct, right? That's what we said exactly in this, which is ABO3. ABO3. Okay. So that's how we calculate. Okay. So let's continue. Okay. So that's what we say here, right? Calcium, tetnut, perovskite. You have corner, 1 of 8. If it's edge, 1 of 4. Face, 1 of 2. Body inside, 1. Okay, so that's how you do it, okay? In this case, we don't have edge, right? Edge is here, so it doesn't matter. So the whole thing will be N equals to M body, because N, you have only 1, you times 1, right? So M face, you times 1 of 2. N edge, you times 1 of 4, 1 of 8 times N corner. Okay, that's the equations from where the equations from. Okay, so let's continue. Okay, so that's what we said. So calcium, which is 1 out of 8 equals to 1. Titanium is easier because in the center, so it's 1 of 1. And oxygen, which will be 6, I have 6 red one here, but you only count as face only 1 of 3, so 3. That's why your is ABO3. And also there's a charge balance here. Okay. So that is the whole thing of the crystal structures of this part 2. So now let's come to the summaries. Okay, the summaries. So first of all, remember crystal structures, you need to have 3 rules. The rule 1 is charge balance, right? Charge balance. Rule 2 is what? Rule 2 is always about the RC over RA, right? Rule 2 is RC over RA. So RC over RA determines the coordination number. Okay, determine the coordination number. But always remember this RC over RA rule applies to ionic case. Very ionic case. If you have a little bit more covalent bond, which is the rule 3. Rule 3. Okay, Cn now change to 4. So even from that table, it's supposed to be 6, but in the end, only 4 here. Okay. And also, please remember the rock salt. Rock salt is very ionic, and the RC over RA is predict that it's supposed to be 6. Correct, it is 6. So it's more or less like 2 FCC interpenetrating each other. That's rock salt structures. And cesium chloride, again, is very ionic, and coordination number is 8. Remember, it's more or less like BCC, but it's not BCC. BCC help to remember. Okay, so it is not a BCC. Okay, so let's continue on. And zinc blend, which is more covalent, and so that's why, because this is a special case. So CN number is 4. CN number is 4. So this is these 3 rules. And then we also learn a little bit about perovskite, ABO3. So A is corner is 1, 8, edge is 1, 4, face is 1, 2, body is 1. Okay, that's ABO3 structures tells you this. If your atoms stay at 1 unit cell, depend on its position. So it's counted as different percentage in that unit cell. Okay, so that's perovskite. Now we move to the, you need some time to copy down or take a photo. Yeah, these are the summaries of this hour. Okay. Okay, so now let's move on. Okay, so the last one, the characteristic of ceramics characteristic. Okay, so move on. So we already learned now from just 2 hours. So we know that ceramic is inorganic and non-metallic. Ceramics are inorganic and non-metallic. And also we already know that bonded by ionic covalent bond, right? And we also, in our more or less like a common sense, we know that most of the time ceramic have better electrical and heat insulations than this metal, right? Even my son is a primary student, he knows, why you use rice bowl, right? You don't use a metal bowl because rice bowl is heat insulation, right? Otherwise it will be very, it's burning your head, your fingers, okay? So most of the time have a better insulation in electrical and heat, okay? And also ceramics brittle, very less ductility and toughness than metals, okay? And also why people love ceramics, why your handphone have 90% of your handphone materials are ceramic, because it's very stable, high chemical stability and high melting temperatures. So this is very, very useful in many applications, okay? And I give you a few special things here, okay? So these are more or less like a common sense for material scientists, okay? But I give you a few exceptions which can have Nobel Prize, okay? So this one is obviously it's a ceramic or not? Tell me, is it ceramic? Lanthanum, strontium, copper oxide. Lanthanum, barium, copper oxide. This one's strontium, sorry. Yeah, doesn't matter. Tell me, this one is a ceramic or not? Yes or no? How can you determine it's a ceramic? Jonathan says ceramic. Because have what inside? Tell me. Have a got non-metal. Thank you very much. Oxygen, right? Oxygen is non-metal, right? Thank you, Fonga. Okay, so this one is obviously a ceramic. But this materials, if you put it in 35K, very, very low temperature, it's going to be superconductor, which means its electrical resistance is going to be equals to 0. Okay, it's become a superconductor. Of course, there's certain condition here, certain condition which is have to be put in a very cold temperature, okay, but no matter what, special, right? Because we always said ceramic is what? Ceramic is electrical insulator, which means the resistance is very, very high. But in that special case, if you put in a very freezing, very low temperature, the resistance is going to disappear. It goes to 0. This one, very unique thing, right? Very special. That's why it's a Nobel Prize in 1987. Okay, for their breakthrough, this is from the committee. This one is a committee word. Okay, for the important breakthrough in the discovery of superconductivity in ceramic materials, right? That's why they can win Nobel Prize, because common sense is ceramic is a insulator. Common sense, okay? But they found this very special phenomenon if you put on a very low temperature, so it's have 0 resistance, superconducting materials. So this is the first example I had to share with you. So let's see the second example. So there's MAX. So M, which is early transition metal. So what are the early transition metal? You can just Google everywhere, okay? Early transition metal is this few. Early means happen earlier, early this transition metal. Okay, group A is this long. X is carbon and nitride. Okay, obvious this one is ceramic or not? Yes or no? Is it ceramic? Yeah, obvious, right? Because you have carbon and nitride, right? Obviously ceramic, okay? Yeah, so once you have MAX, okay, so actually this one is, for example, like a titanium silicon carbide. So this one become what? Become electrical and thermally conductive. It's a special thing, become electrically and thermally conductive, and not suspend or thermal shock, because most ceramic very suspend or thermal shock, which means if you give them very high gradient thermal gradient, so it's very easy to crack, okay? And it can even get machinable. You can even cut it, machinable, and very specific stiffness and very chemical stable, which means now it's more or less like they have the good thing of ceramic. They also have the good thing of ceramic is chemical stable, right? Chemical stable, and the good thing is stiffness is very high, right? And also very good for some. Sorry, not this one, right? So they have the good thing of ceramic, but they're more or less like a metal now. They can be machined. They're not susceptible for the thermal shock. They even have a bit of conductivity in electrical and thermal. Okay, so again, it's a special case. Some special cases. Example 2. Continue. Okay, so ceramic is so useful everywhere. So as I said, like insulation, it can be used as insulation, like a high temperature furnace, like fibers, silica, aluminum, or even a little bit conductive, like aluminum nitride used in the electrical packaging heat sink. Okay, and for example, like this case, right, this one is used in NASA. So it's a silica fiber. This is silica fiber. So more or less like shuttle ties. So they're going to have a lot of pores inside, right? Because air is a very good insulator. Okay, air. So they just use these fiber structures, put air in between, trap the air in between, to make it super insulation. So this one used in the space. This is a space shuttle to just insulate the heat from the burning sun. Okay, and offer low heat conduction. Okay, and also, for example, like space shuttle, thermal barrier, high temperature windows, so these are ceramics. Okay, because ceramic compared with the metal have much higher high temperature stability, and also can be used as electrical and dielectrical. For example, iron conducting, lower voltage insulator, hostile, semiconducting, IV characteristic, almost everything, right? So ceramic, as I said, it's one of the most widely used electronic materials in the modern like handphone and computers. So it's so useful. Okay, so I just give you examples here. And also can be used in the magnetic, such as hard magnets and soft magnets, like ferrite magnets or transformers cones, like soft magnets, and also superconductor, as just we said, the YB30. This one just we said is a Nobel Prize one, right? Nobel Prize YB30. Okay, and also used in computers, like insulation, as I said, 70% of materials in your computer is ceramics. So for example, like heating elements, thermometers, dielectric insulation, and piezoelectric, and everything. Okay. And this is piezoelectric and the magnetic ferrite. Okay, so you can just search the reference book. Okay. And the few videos you can also search from there's tons of videos there, so I just leave you to explore. Okay, and also like optical can be used as a transparency, like cables for optical communications, ultra pure silica, like Windows soldering glasses. So if some of you went to my 8.3 material summit in your year 1, so you must remember this one, right? The silica fibers, right? This one is again a Nobel Prize 2009 Charles Kao. Okay, Nobel Prize, because as I said, this one changed the world. The internet you use optical fiber, it's all used by this one, optical fibers. Okay, it's a silica. It's more or less like your rice bowl, same materials as your rice bowl, a silica ceramics. Okay, but it's very soft, right? You remember if you went to the 8301, right? The course, some of you went, I know. And this one, this is the same color one, right? Optical fiber, like more or less like here. Okay. Okay. So it's a silica fiber. Okay. It's a pure silica, but it's more or less, although it's once becomes so thin, it's more or less like here. Okay. Silica fiber. Okay. And continue, even ceramic, like this one can be very porous, very dense, and transparent ceramics. Okay. A lot of things. Like your bowls can even make that transparent. Okay, there are many things you can do there. Okay, and can be used in nuclear applications like fission and fusions. So these are some ceramic materials. Okay, so that's, and also yeah, I mean Singapore is thinking about using nuclear powers, but yeah, I think it's under discussion. Okay. And the chemicals can be used as biocompatibles, like artificial joint, like bones. Your bones are all ceramic, right? So when aging, so it can be used as artificial bones and heat exchange. And like this is the bones, the hips. This is the hips, okay? And your teeth, all this can be used using ceramics, okay? So that is the all thing of the last part. So the last part actually is not examinable. Okay, no worry. So this part is not examinable. So just let you know. So there's certain things there. How can I turn off this one? This one is not examinable. So just let you know, ceramic is important. There are many things you can learn. So for this course, it's just share with you. So there are so many things waiting for you to explore, but many have in-depth knowledge. So most likely you will learn in your PG class, okay? So in this course, we talk about the most general things for ceramics, such as processing, like use sintering, and how can we solve the toughness issue? Because when you use, right, you have to be very careful. Once the material gets brittle, gets shattered, so you can't use it anymore. So how can we solve this issue? Okay, so that is all for today. So let me share with you the timetable. It's a bit this year is a bit different. Here, let me stop the